Hello everyone, this is session 6 and it's systems engineering. So let's begin with that session. First of all, I'll give you a little history on systems engineering. The concept began in the late 1940s at Bell Laboratory. Kind of an obscure note in history. Systems engineering really became prominent during the time the National Aeronautics and Space Administration was created. So NASA had a very distinct requirement to make sure the development of its systems was thoroughly ready for the astronauts to use, to make sure safety and the technology and everything was correct. So systems engineering pretty much has its origin in NASA and the early missile flights and development that were done in the United States. From there, the military took the concept of systems engineering and used it quite heavily in the development of its weapon systems. So the principles and techniques of systems engineering have grown substantially over the years, borrowed from NASA and then in military development. What you're looking at here is what is called the IPPD, Integrated Product and Process Development. And essentially this term was coined back in the mid to late 1990s. Prior to that time, there was no concept called IPPD within DoD, and the closest thing to it was called concurrent development, concurrent engineering. And concurrent engineering is the management of engineers predominantly within a manufacturing setting. So DoD recognized that they needed something to capture the entire developmental process, to tie people to the functions that were used to develop systems. Therefore, they came up with this term IPPD. And as you see in the definition there, it's personnel management and communication that ties all these areas together. So it's very much related to systems engineering. And to give you a functional definition of systems engineering, there on the bottom you see it. It's a problem-solving methodology that ties all those functions, as you see in the IPPD, together. It's not exclusively electrical, mechanical engineering. It's more than that. It's everyone that is involved within the developmental process of a system. So we're looking at all the technical areas, in addition to the money, in addition to the schedule, and so forth, to try and make sure that things don't fall through the cracks. So in a typical large program office, you have the PM. The PM is busy communicating. The PM is taking care of the program. And you also typically have a deputy program manager. But the systems engineer holds a very powerful position within the program. Systems engineering is the glue, the synergy that ties all the functions of the program collectively together. Now, without that process, things could be broken, and so in the IPPD, we're asking for everyone's opinion as a participant to help resolve any problems from becoming problems, to prevent those things from becoming problems, to surface issues and things like that before they become problems. So that's why you're seeing here an illustration of the participants who can provide information in their respective areas to help resolve issues from becoming real problems. There you see cost, manufacturing, quality, logistics, a couple areas under logistics, reliability, maintainability, and I'll cover them later on in Chapter 9. Environmental and safety, human systems integration, interoperability, open systems, and then software engineering. So everything collectively comes together under the systems engineering process. I'll try to show most of these illustrations in the subsequent slides. There are some that are not defined. For example, interoperability has different characteristics. You have physical interoperability where one, let's say, metal component meets another metal component, and you want to make sure they're operating together as they're supposed to. There's electrical interoperability where one electrical component interfaces with another electrical component, and you don't want to have the wrong voltage or something like that. So it's a way of making sure that one component or one subsystem meeting another component or subsystem are operating correctly. Open systems, a lot of people use that term. It was originally created as an architecture, and it's called Open Systems Architecture. Now, the history behind that one is basically every computer engineer would like to have the capability where all software programs and where all hardware programs collectively work together. But the fact is, they don't. You know, software systems that, softwares, for example, that don't interface with each other. And you know, hardware systems that don't interface with each other. So theoretically, open systems architecture is pie in the sky. And one day, perhaps, we'll get to that point in engineering to be able to have a true open systems architecture where all the electrons will work with every other electron, all the software will work with all the other software, and all the hardware will work together with each other. But unfortunately, we're not at that point. Every time I meet a software PhD, I ask them, how close to open systems architecture are we? And they always give me the same answer, 4 or 5 more years away. So who knows? And maybe one day it might not be possible ever to get there, but we'll see. So open systems architecture, in the meantime, DoD has had a theory of open systems architecture, and they've had regulations for open systems architecture, and they basically say, okay, DoD, you're only going to use these software programs and these hardwares to achieve an interim open systems architecture. So it's a very problematic area, and there are numerous regulations that cover that. Here you see it says systems engineering is a top-down approach to functional decomposition. That word decomposition means basically the job of the systems engineer is to break down a hypothetical system into manageable parts and pieces. So if you look at the diagram in the center, you see that's what's happening. We're going from a system level, then going down to the subsystem level, going down to the component level, to the nut and bolt level, and I like to say down to the goo level. So we're trying to initially, early on in the life cycle, conceivably think through the problem. For example, suppose the Marine Corps has a requirement for a new troop transport. Now, I said troop transport, and normally when you think of troop transport, you think of rolling stock. But conceptually, when it's determined that a deficiency exists as a material solution, someone proposes that problem be taken care of. And on the Army side and on the Marine Corps side, it's historically been called combat developments. So you have combat developers who write the early documentation. They write the ICD and CDD and AOA and all that kind of stuff. And theoretically in that process, they're supposed to define the customer's requirement. They're not supposed to jump to a system level. So what I'm saying is, you're not supposed to say, we have a problem and therefore we're going to choose an airplane. No, you're supposed to say what the problem is, and then in the concept phase, try to define what type of technology the customer would need in order to get the appropriate system. And in the transport case, well, sometimes it may be a new truck. Sometimes it may be a new helicopter. Sometimes it may be a new airplane. But the point is, we go through the process of defining what the customer wants. Now, once we know what the customer wants, then, and in our case, let's say the customer does need an aircraft. Here we have, at the system level, it would be talking about the system's overall capability to fly, to move, to hold people, so forth. From there, you break the system down. All right, on an airplane, you've got the end item itself, you've got the frame, you've got the engine, you've got all the other components. So you break those subsystems down into manageable parts and pieces. And just like the structure's showing here, it literally goes down to the nut and bolt level and down to the chemical composition. Now, we can't do that right away at the onset of our program. It takes time to get to that level. So this picture here is a snapshot over time. And on the left-hand side where you see the specifications, I have my little SPUD PM. Years ago, it was just an easy way to remember these different specifications: system level, performance level, detail, process, and material. And in essence, that's what the SPUD PM does. It captures all the information as a contractor is developing our system to the point where the system now is fully developed and the customer gets it and they're happy. And from all this information, systems engineering captures all this information in a large computer database, a repository, because once the system is fielded to the customer, there probably are going to be changes that will occur. So we would go back into this database here to see where the problem lies and then to make fixes to certain areas, because this effort helps identify a major portion of what you'll see later is called the Technical Data Package, or TDP. So we have a large effort just to put all this together on the part of the contractor, and over here you have what are called baselines. These are not management baselines like cost, these are engineering baselines, and they're called the functional, allocated, and product baselines. And we have specific reviews and audits to look at these baselines. So the government will get together with the contractor and they'll start with the first one here. They'll go through the functional baseline, the allocated product, so forth. Not every system is going to be developed necessarily this way. It all depends, but the larger systems pretty much use this process.